So, good afternoon, everyone. I am Soumyaranjan Ratha, a postdoctoral fellow in Akita University, Japan. Now, I'll be presenting on development of bismuth ferrite-based multiferroic thin films and how we can use this to reduce the energy consumption in magnetic devices. So, first, I will give a short introduction about the multiferroic materials. As we know, these are the materials which can show uh, ferromagnetic and ferroelectric properties in one phase. And here how I can exactly use this in devices, like I said, there is ferromagnetic and ferroelectric. So I can switch one by another. So it will be very simple to operate. As a result, there will be very low writing power, very simple element structure, and the energy consumption will be very low. And the very important thing is that there is no noble material. So how exactly we can use these devices? Like we know the recent and the latest device in magnetic device is the rest memory. As we know in the rest memory, we can store data that is 100 terabytes capacity. And that is very higher capacity than hard disk drive. But there is a problem. In the problem, while we are writing data, as we know, we need coil to write the data. So consuming coil, like we have one nanowire, for that we need one coil. But exactly we can't say that IBM will be using this idea. This is the conventional idea to write data. If IBM will think to use this idea, then that is very high energy consuming. So how to solve this problem? Like you can see here, I showed and like I said, in the IBM, if we'll be using the coil to write data, instead of this, sorry, instead of this coil, I can introduce a multiferroic thin films. And how exactly I can write data in the multiferroic thin films, like there is ferroelectric polarization, I can create this polarization by giving electric voltage different, and it will create magnetization. As a result, I can write data in the nanowire. So this is the patent we have made, and now we're working how to get the material for this application. The important thing here, we need some material with very high perpendicular anisotropy and high saturation magnetization. In the second case, we are working on magneto-optical modulator, which is optical device. As we know, in the case of magneto-optical modulator, we write data here by using spin current. And in general, by using spin current, we consume lots of energy. So here also, we can think about multiferroic thin films to solve this problem. Let's see how we can solve this problem. Like I said, this is the general concept of the data writing by using spin current. So instead of that, we can simply use a multiferroic layer and we can write data by using light polarization by using the concept of Moog measurement. So here we need some material that will give very high core effect and the core angle should be very high. In the third case, we are working on a sensor devices. Here I'll be presenting three devices and I will show three material for respective devices. So this is the third device, a sensor device. In sensor device like TMR, the sensitivity is very high, but the signal output is very low. So how to solve this problem? We came with the first solution. If we use a multiferroic layer, then we can detect the signal. But the problem here, it can detect only large magnetic field. But if there is the magnetic field that is very small in power, then it cannot detect. Now think is how to solve this problem. So we came with some other idea, some little modifications. By using a ferromagnetic layer on the multiferroic layer, we can solve this problem. When there is no external magnetic field, there is no output signal. But when there is a small magnetic field, this ferromagnet can detect. And here there will be a higher magnetization and it will switch magnetization in the multiferroic layer. As a result, we can sense the small magnetic field also. But for this kind of application, we need some multiferroic material with high saturation magnetization and low coercivity. So considering this, we started working on bismuth ferrite. As we know, these are the materials which can be operated in room temperature. It has very high Curie temperature. And the problem here is the antiferromagnetic G-type structure. But by doping something, the normal concept is by doping something, we can solve this problem and we can improve the properties. Like I said, I am working on three devices. In the three device, I need certain properties like I explained, saturation magnetization, perpendicular anisotropy, co-rotational angle, again perpendicular anisotropy, low coercivity, and high saturation magnetization. So this is our fabrication technique in which we give priority to pulse DC sputtering method, because in the case of pulse DC, we have the evidence how we are getting high crystallization. So I'm not going detail into the fabrication technique. But the problem here, this is the first material we tried by using barium in A side, and there is no element in the B side, but there is in-plane magnetic anisotropy. As we know, for magnetic sensor device, magnetic memory device, we need a material that will be showing out of plane magnetic anisotropy. So this material failed to be a candidate material. Then again, we started studying like substituting lanthanum in A side, cobalt in B side, and here we successfully found perpendicular magnetic anisotropy, and this can be a candidate material. But thing is here, we substituted lanthanum in A side and cobalt in B side. So now cobalt we substituted, but we have to optimize the cobalt concentration. So we studied the dependence of magnetization and anisotropy on cobalt. And we found in one case, if we substitute cobalt, you can see here, the cobalt is increasing the magnetization while nickel is decreasing the magnetization. We had again tried nickel also. In the second case, the opposite thing happening, but we give priority to cobalt because here perpendicular is low, but not so low. So we consider that we will be substituting cobalt in B side and some lanthanide elements in A side. So here again, we started working by changing different elements in A side and keeping cobalt in B side. So let's see whether I'm getting the candidate materials or not. Actually, this is the first part of my study. So here I'm presenting only the first part, like finding the candidate materials. So these are the basic features of our sputtering devices. The most important feature here is the VHA plasma. I'm not again going detail about the VHM plasma. So this is the XRD data where the BiFeO peak is shown here. Of course, this is not so clear, but the BiFeO was formed. The problem here we found in the case of erbium, dysprosium, gadolinium, the peak is not so prominent. In the second case, when we measure the VSM or the ferromagnetic loop or hysteresis loop, we found in the case of a neodymium, the saturation magnetization is very high. That is better for magnetic memory device. In the case of europium, the coercivity is very low and saturation magnetization is also relatively high. That is better for sensor devices. And then we studied their magnetic property or perpendicular magnetic anisotropy. You can see here we have used the CF Stoner-Wolfert single domain particle. And by increasing the angle difference, there is an increasing in the coercivity and squareness as well. But in the case of, again, erbium, dysprosium, gadolinium, there is a downward trend. Like I showed in the case of XRD, it has problem. In the case of perpendicular anisotropy also, it has problem. So second, then we studied about the optical device by using the Mock measurement system, and we found by substituting lanthanum, we can find highest core angle. So after magnetic property, we studied the electric property or ferroelectric property, and we found almost all the material is showing ferroelectric property at higher voltage. But again, in the case of gadolinium, dysprosium, erbium, there is high leakage current, you can see after around 40 voltage. So in this case, we found one thing. In the case of XRD, the peak is not prominent. In the case of perpendicular anisotropy, it is not showing perpendicular anisotropy. And in the case of a ferroelectric curve, there is high leakage current only in this three element. So here we investigated why it has problem, and we found it's because of the oxidizing tendency. So this is the graph of the oxidizing tendency, and this is the order. Here we proposed a idea. Like when we dope something, when we substitute something, it has an oxidizing tendency and it attracts the oxygen from the phase and it creates a defect or vacancy. So that is the problem of the lower properties in the material. So this is the evidence from the XPS, which is clearly found that you can see here, this is erbium. In the case of erbium, there is a leakage current and oxygen vacancy is higher. But in the case of europium, there is no leakage current and also there is very simple or very less oxygen vacancy. So from this study, we again proved that we have to substitute some element with low oxidizing tendency. So this is a summarize of the first finding, like we substituted neodymium, and we can say that this material is better for the magnetic memory device. In the case of for lanthanum, this is better for the optical device. In the case of europium, this is better for the sensor devices. So after finding this, we have to find their grain structure, domain structure, and we found the grain structure, domain structure is like comparable to ferromagnet and ferroelectric materials, but not so low. In the second case, we studied the magnetization switching, and we successfully showed that there is magnetization switching. That means there is magneto-electric coupling. We are unable to study the magneto-electric coupling directly. That's why we took the help of EFM. So we could show here, it is showing magnetization. In the second case, we also showed the magnetization transfer, because after writing data, the data should be transferred from the multiferroic layer to nanowire. So here we considered the metal as cobalt palladium, and this BFO material was BLFCO. And here we found there is a switch of 75%. Of course, this is not 100%. So now it's a challenge for us how we can find a switch of 100% of data switching. So in the Curie temperature, we found we have enhanced the Curie temperature till 450 degrees Celsius. So considering all, we confirmed that these are the materials which can be a candidate material for the devices that I proposed. So thank you very much for your patience and attentions.
Thank you very much for a nice talk. So if you have any short question, I can accept one. If not, because the schedule is behind, we would like to move on to the next speaker. Okay, so thank you very much.